Okay, welcome everybody to this new seminar of the IM series. I'm very pleased to have with us Boris Hanin. He's an assistant professor at Princeton ORFE. He's working on deep learning, probability, and spectral asymptotics. Prior to Princeton in 2020, he was an assistant professor in mathematics at Texas A&M and an NSF postdoc at MIT Math, and a PhD student in math at Northwestern University. His funding is supported by an NSF career grant, DMS 2143754, and NSF grants, DMS 18555CX4, and DMS 2133806. He is also a consultant for an ONR Muri on foundations on deep learning. It's with extreme pleasure that I leave the floor to Boris. Please go on.
Okay, thanks a lot, Flavio. I hope you all can hear me fine. Let me just, okay, very good. I think everyone can see my slides. Okay, so thank you very much for the invitation to come give this talk. It's really exciting to talk to such a broad audience, and because it's such a set of diverse backgrounds, I'm going to try to keep the talk rather self-contained, and I won't assume too much prior knowledge about neural networks. So what I want to kind of convey today in this talk is that people talk about neural networks, or equivalently they say deep learning, but it's not 100% clear what the role of depth is in deep learning and what is really deep. I'm going to try to explain kind of what is the deep of deep learning. Okay, so the basic outline for my talk is the following. The first part of the talk is basically just an introduction. Like I said, I don't want to assume that people already know exactly what neural networks are and how they're used in practice. And so I'll briefly go through that. I'll explain in the simplest instance what a neural network is. I'll focus on fully connected networks. Then I'll tell you a little bit about how neural networks are used in practice, because by understanding this, I'll be able to focus on some of the important practical questions that really motivate the mathematics that I tend to do in studying neural networks. Okay, and then in the second half of the talk, I'm going to try to understand how these practical questions work from the point of view of what is the effect of depth? How does it help us to have deeper networks? And I'll mainly focus on kind of two areas of mathematics. One is the effect of depth in approximation theory. That'll be a relatively brief discussion, but I at least want to highlight some of the interesting work that's been done in that direction. And then I'll really try to advocate that the real way to understand depth in practice is to understand it through its role in initialization and optimization of networks. Okay, I'll explain what all that means in just a moment. So I know that there are comments that are enabled on YouTube, so I will try my best to keep track of the comments. So if you have questions, just feel free to put them in the chat, and I will try to answer them as soon as I see them. Okay, so let's start. What is a neural network? Okay, well, at a very high level, a neural network is just a parameterized family of functions. And to tell you what kind of family of functions I'm talking about, I need to make a kind of formal definition. Okay, so I'm going to tell you about the simplest kind of neural networks. They're called fully connected networks. And my notation is the following. So these are going to be functions that I'll write z l plus 1 of x and theta. So x here are the inputs. These are functions from Rn0 to Rnl plus 1. And theta is going to be a collection of parameters. And the notation will kind of become clear right now. So what kind of functions are these? Well, they're actually relatively simple-minded functions. So let me just kind of walk you through what this definition is saying. So to produce an output from an input, you start with x, which is an n0 dimensional vector. And the first thing you do is you apply a matrix to it. So W1 is an n1 by n0 matrix, and it maps you just in a linear way from the input space to some other space, which has dimension n1. And then you apply a fixed nonlinear function sigma to each component of the resulting vector. So when I write sigma applied to a vector, that just means apply sigma component-wise. Okay, so the name in neural networks for applying a linear transformation and then applying a nonlinear function to each component is called a layer. So that's one layer of the network. And when people talk about deep neural networks or deep learning, what they mean is that there are many layers. So my notation is that there are capital L layers, capital L times that you apply an affine transformation, or a linear in this case, and then a nonlinear function to each component. And then the output of the network, z L plus 1 of x and theta, L plus 1 reminds me that I have L plus 1 times I apply a linear transformation, is just a linear function given by multiplying by my final weight matrix, W, are called weights, in layer L plus 1 applied to the result of the first capital L layers. Okay, so whatever I've said, I haven't completely lied to you. A neural network is just a parameterized family of functions, and the lingo is kind of like this. So this number capital L is something you have to specify in the definition of a neural network, and it's called the depth of the network. So when people talk about deep learning, they just mean L is relatively large. That's the colloquial usage. So the dimensions of these matrices, so the dimensions of the intermediate spaces through which you process the input x, are called the widths of the network. And this fixed nonlinear function, sigma, is called the nonlinearity, or sometimes the activation function. Okay, so altogether, these three parameters, the depth, the width, and the nonlinearity, define what's called the architecture of the network. And in this way, they determine the form of the function that's computed. And then what's left is this vector theta of parameters. And the point is that the vector of parameters theta is just precisely given by specifying the weight matrices W themselves. Okay, so for each setting of the weight matrices W, I have some particular setting of the parameters theta, and I get some particular function from Rn0 to Rnl plus 1. And as I vary theta, I get different functions. Okay, so maybe let me just end this first introductory slide by saying that the most popular choice of nonlinearity in practice is what's called the ReLU. So each time you apply the sigma, it's just the maximum of whatever the input is and 0. So basically the way you read a ReLU network, which just means a neural network where sigma is equal to the ReLU, is every time you apply an affine transformation, one of these W's, you look at each component, and if it's negative, you zero it out, and if it's positive, you keep it. Okay, so in this way, you just make a piecewise linear function of your input x. Okay, so that's what a neural network is. And what I want to do now is I want to draw a couple of pictures for you, and then tell you a little bit how neural networks are used in practice, mainly focused on these pictures, which is really like the intuitive way I think about it. Okay, so a neural network, whatever it is just a parameterized family of functions. And I've recapitulated the definition at the top of this slide, right? You give me an input x, and sometimes, just for brevity, I drop the superscript L plus 1 on the definition of the neural network. And you process x through a bunch of layers, and you get a linear output. Okay, so the way I think about it, though, is that on the left, it's just the space of parameters theta. This is the way a computer views a neural network. You have to specify a long, long list of numbers theta. And then once you tell me the thetas, that means you've told me these weight matrices W, and you've given me some particular function. But because the map from the inputs x to the outputs is very nonlinear, and it's also very nonlinear as a function of the thetas, I think on the right, as there being some complicated manifold of functions, changes the value of the parameters on the left, you move around in a complicated way in the space of all functions. Okay, that's what this picture is supposed to connote. And the key intuition, if you take nothing else away from this talk, is that if you were to ask me what's the most important thing about neural networks, like why are they so useful in practice? Well, for me, the reason they're so useful is that the vector of parameters that we normally use in practice is just massive. It's very common to have, for example, 100 million parameters in a neural network. And so these spaces of functions that you get, these kind of funny manifolds that I've drawn on the right, are so large that you can basically think of large neural networks as giving an interesting way to parameterize almost any function you like. And kind of the magic, in some sense, of modern machine learning is that there's actually numerically stable and scalable ways of searching over essentially the space of all functions using these neural networks. Okay, that's kind of my high level introduction to what exactly is a neural network. Now, I want to tell you how this search works. That's what the next slides are about. How do you actually use a neural network in practice? Okay, so let me see if there are any questions while I'm doing this. Okay, cool. Okay, how do we actually use one of these neural networks? Well, let me tell you how to use neural networks for what's called supervised learning. Okay, in supervised learning, the setting is the following. Somebody gives you a data set script D, and that just means a collection of inputs xi, and then the values of a function f evaluated at these inputs xi. So the way that one should think about it is f is a function that you don't actually have a good formula for. So think, for instance, that xi is a picture that you take with your phone, and f of xi is whether or not there's a car in the picture. So it's something that the human brain can compute rather accurately. We're good at detecting cars. But to a computer, it's a rather complicated function. You know, the image xi is just a collection of pixel values, and it's not clear how, given the pixel values, to compute whether or not there's a car in the image. And indeed, the goal of using neural networks for supervised learning is to try to find a good approximation for this otherwise unknown function f. Okay, so the way you do this is the following. So step one is you choose an architecture for the network. Okay, you fix the depth, and you fix the widths, and you fix the nonlinearity sigma. And this gives you some family of functions over which you're going to search. And again, I've drawn it in two ways, just like on the previous slide. To a computer, you're going to search over the space of parameters theta, i.e. you're going to try to set the weight matrices in a good way so that you hope to find a good approximation to the underlying function f. Okay, and I've been optimistic in this picture. I've tried to draw, at least on the right, some place where either f is exactly representable by the neural network architecture that we've chosen, or f is maybe approximately representable. And our goal is to say, okay, we would like to find a setting of parameters theta that gets us close to that function f that underlies the data generating process. Okay, so how do we actually go about searching over the space of functions? That's what the next steps of the typical use are all about. And this is all about optimization. Okay, so the first step in optimization is you randomly select a value of the parameters. So mathematically speaking, what do? You fix a probability measure, which I've denoted by script p or blackboard p sub theta naught, on the space of parameters. These probability measures, as I'll explain in a couple slides, tend to be extremely simple-minded. Just all of the parameters, all the entries of the weight matrices are IID Gaussians. Okay, then you sample from this distribution. You get some particular value for the parameter vector theta naught. And this gives you some rather complicated distribution over the space of functions. So if you look on the right-hand side of the slide, I've tried to draw as a cartoon a complicated profile for the resulting distribution. And it's complicated precisely because the map from parameters to functions is a rather complicated map. Okay, so this random choice of the setting of parameters for the start of training just gives us a place to start optimization. And for now, it knows absolutely nothing about the underlying function f, because we haven't used the data at all. We haven't actually used that we know the values of f at some points. Okay, so that's the last step of actually using a neural network in practice, is you iteratively improve your guess for starting from theta naught, and you try to get to the function f. Okay, so what do? You do optimization, almost always by a first order method. And the way I read this is you introduce a loss function L. For example, you can think of it as just something like the sum of the squares of the differences between what you currently predict using the neural network with the value of parameters given by theta, and what you're supposed to predict given to you by your training data. Okay, so your goal is going to be to fit your training data, and therefore, in this context, just to minimize the function L. And you're going to do this by a first order method, where if you're at some point theta t after t steps of optimization, you take a small step in the direction of the negative gradient of the loss function, and that's theta t plus 1. Okay, so I've tried to draw this on both sides of the picture, where the computer implements this as a path in the space of parameters, where you slowly adjust the parameters theta to try to hopefully minimize the loss more and more and more and more. And then this corresponds to some trajectory in the space of functions, where you're moving around in function space and you're hopefully trying to get closer and closer to the unknown function f. Okay, so like all the things I'm going to say in this talk, everything I say here is a little bit of a lie, but it's not too much of a lie. Okay, I've just tried to simplify. This really is, at least at like the 0th order of approximation, what people typically do in practice to train a neural network. Okay, so I've told you that a neural network is this complicated, potentially very large parameterized family of functions. And I've told you that the way we train neural networks is a little bit insane if you think about it. It's just a kind of greedy local search from a random starting point. And the fact that this works at all is kind of amazing. It contradicts a lot of classical principles coming from optimization and statistics that suggest that searching over very large dimensional spaces of functions is rather hard, and somehow that you're going to run into the curse of dimensionality, that you shouldn't exactly fit the data, that you should regularize the loss, and so on. But you don't do this typically in practice. At least it's not very important for making neural networks work well. Okay, so that's my summary of how to use a neural network in practice. And now to complete the introduction, I just want to tell you a little bit, what are like some high level, both practical and mathematical questions that people are excited about to try to understand neural networks. Okay, so I call this slide rather, optimistically, I would say, big questions. Okay, so the first kind of set of big questions is, I just told you, neural networks are so large. I mean, it's really crazy. Like I said, you could have 100 million parameters. Some of these very large language models, like GPT-4, is gonna, I don't know actually how many parameters it has. I don't remember, but I wouldn't be surprised if it has close to 1 trillion parameters in it. These models can just be so large that they effectively, like I said, search over all functions or almost all functions. And then the crucial mathematical, but also practical question is, how do neural networks, as they're used in practice, actually go about searching over the space of all functions? And I think of there as being kind of 3 sub-questions, okay, at least 3. So the first is how to describe what happens at initialization. And initialization is where the optimization begins. It's when you select the network parameters at random. And so the mathematical question here is, describe the probability distribution you get over the space of functions at the start of training. This kind of tells you what kind of functions do I tend to start off with. Okay, then question number 2 is a kind of dynamical question. How does optimization look like in the space of functions? I know how it looks in parameter space. In parameter space, what I do is I just move my parameters to slightly decrease the loss at every step of training. But because the map from parameters to functions is so complicated, we would like to know, at least in some human and computable way, what is the way that neural networks are implicitly searching over the space of functions? And definitely inside of this idea that they search in an interesting way is the reason that they work so well. If you were to just do a brute force search, you're never going to actually find the kind of functions that you're interested in. There are too many functions out there. Okay, and the final kind of set of questions, which is the practical version of the first 2, is how to do what's called hyperparameter optimization. So I won't focus too much on this. This is kind of a separate talk, but one of the things I work on a lot is, if you've ever trained a neural network, you know that to actually get a neural network to train, you have to make a million different choices. You have to choose the architecture of the network. You have to choose how to initialize the network. You have to choose the learning rates. You have to choose a bunch of other parameters. And doing this in a good way often causes you to learn a very nice model based on your training data. Doing this in an arbitrary way, you're never going to learn anything useful. And so because it's so complicated to actually use a neural network in practice, people tend to think of, at least sometimes people will think of neural networks as being like alchemy. They'll say, you do some random things and then it works out, and we'll never understand why. Okay, that's certainly not my point of view. You do things that seem random, and they seem random because we don't have a nice language yet to describe them. And so there's a lot of beautiful mathematical questions to just ask, what are the right ways of thinking about neural networks? And this is secretly what this talk is about. From this point of view, I will try to argue that the way people think about depth in deep learning is not completely right. And there's a better way, motivated by actually proving some theorems, that explains what the effective depth of a neural network is. Okay, so that's kind of set of questions number 1. How do you search over the space of functions? And the set of questions number 2 is kind of, okay, related to number 1, but kind of goes beyond the search procedures. And it really tries to answer the question of, why is it that often in practice, when we learn a function roughly in the way I've outlined, we tend to learn interesting and useful functions. So it's really a question of, can you describe mathematically which function spaces tend to be learned, and how those function spaces depend on the training data that you use, depend on the architecture that you use, depend on the choice of optimization procedure, depend on all the things you have to do in practice. It's a really, I think for me, a beautiful set of questions. And I won't talk too much about it, but let me just say, because I kind of can't help myself, that one of the most important things about neural networks in the way they're used in practice if you were to stop someone who's a neural network practitioner and say, why are neural networks so great? What do you actually use them for in practice? A lot of people would say the most important thing in practice is what's called feature learning, or sometimes called transfer learning. It's the following kind of idea. I'm just going to explain it in this very short equation. So what I've written here on the right is just the ith output, that's the subscript I, of a neural network evaluated at an input x with parameter vector theta. And I'm just writing out explicitly that the output of a neural network is a linear combination with coefficients given by the weights in the final hidden layer of the output of the final hidden layer of the network, which is your nonlinear function sigma applied to what happened in the network up to layer capital L. And the reason I'm trying to write this formula is just to note that, just by looking at this, because you train, i.e. get to change the weights in the final hidden layer, and you get to change all the previous weights as well, you can think of training a neural network as simultaneously learning both a basis of functions. That's what these sigma of ZLJ of x theta are. You can think of them as learned data-dependent basis functions and the coefficients at this basis of functions. Okay, so this is the idea that neural networks are not linear models, and they go way beyond linear, and you somehow both search for a space of functions over which to approximate your data and simultaneously find a good setting of coefficients in which you're going to actually do the approximation. Okay, so neural networks are nonlinear, and it's therefore hard to understand them, but that's certainly a part of their power. Okay, so that's the end of the kind of overview introductory part of the presentation. So I'm going to again stop and see if people have questions or comments. I don't think people have put any more questions in the chat, but I'm happy to discuss or just leave until the end of the presentation. Okay, so no one seems to be putting anything, but I'll keep an eye on it anyway. Okay, so let me now transition to the second part of the talk, and I'm now going to focus on a particular question that I find to be extremely interesting, namely, what is deep and deep learning? How do you think about the depth of a neural network? And I'm going to try to convince you that it's not obvious. Okay, so I'm going to tell you about the role of depth in two kinds of ways of thinking about a neural network. And first, I'm going to just sketch very briefly, because I think it's interesting, the role of network depth when you think about pure approximation theory. So here you say, I don't care about the way I train neural networks in practice. I'm just trying to describe what kinds of functions a given neural network can compute. Okay, and I'm just reminding us at the top of the slide that the kind of neural network I'm thinking of is just one of these fully connected networks, right? You apply a weight matrix, you apply your nonlinearity sigma to each component. You do that capital L times, and then you have a linear readout. That's the kind of approximation theory I'm interested in. Okay, so maybe the starting point, the most classical approximation theory result about neural networks can be stated like this. Okay, if you fix the depth of the network, you fix the number of layers L, and you just let the widths become larger and larger, i.e. the dimensions of these matrices W can become bigger and bigger and bigger. That's something you get to choose. Then there are very robust theorems which say you can approximate arbitrarily well any function you like as long as the network is wide enough. Okay, so these theorems go back to the 80s, and they don't actually tell you a difference between deep networks and shallow networks. From this point of view, even one hidden layer is enough. Okay, but then when people around 2011, 2012 started using deep neural networks, well, what they found is that actually, if you look at the approximation theory with deep neural networks, something cool happens. Okay, and there's many papers about this. Okay, I wrote some stuff about this, but my favorite papers are by Telgarsky and by Yarotsky. And if I were to just summarize all these theorems as one theorem, what they prove is that, yes, infinitely wide networks or arbitrarily wide networks can essentially approximate anything. Oh, I see a question. Can we use a different loss function instead of L2? Yes, okay, that's an excellent question. So let me say, I used L2 only just for illustrative purposes. In practice, you use all kinds of loss functions. For classification problems, for example, you use things related to cross entropy or exponential type losses. It's just some way of measuring the distance between your current predictions and what you're supposed to predict. So nothing I say is very specific to L2. Yeah, great question. Okay, so what Telgarsky and Yarotsky and lots of people prove is that if you count per parameter, actually deep networks are better than shallow networks. So if you allow yourself to go to large depth, you can approximate many classes of interesting functions way more efficiently per parameter. And so people thought originally, maybe that's why deep is good in deep learning. Maybe in practice, the reason we need deep neural networks is they're just more efficient at approximating interesting functions. Okay, so there was a collection of results which basically said there exist interesting classes of functions that you can approximate more efficiently with deep networks than with shallow networks. And then, okay, there were some results that I proved together with some really wonderful collaborators, which I have listed here, which at least, okay, in relatively simple settings, but like functions of with input dimension 1, that's what we did. Although I'm sure it's true for other input dimensions. We proved the kind of converse to it, which is not only do there exist functions that deep neural networks approximate much better than shallow networks, but in fact, you don't lose anything. Any function you can approximate with a shallow neural network, you can approximately equally well by counting number of parameters with a deep neural network. So somehow deep is strictly better from the point of view of approximation theory. So that's very interesting, and that sort of made us happy. But at the same time, people were doing all kinds of empirical experiments. Okay, and there's a beautiful paper, which I strongly recommend people look at if they're interested in this kind of thing, written by Ba and Caruana, called Are Deep Networks Really Deep? Or something like that. And what they found empirically is this really cool effect, that they actually went and they trained a bunch of deep networks to learn some really interesting tasks. And then what they showed is that those same functions you learn with deep networks, you can also learn by shallow networks. It was just a little harder to get the optimization to work. Okay, question: how many layers does a network stop? Yeah, so there's no agreed upon definition about how many layers is deep, but typically what people say is a shallow network has one hidden layer, so it corresponds to capital L equals 1. And as soon as L is greater than or equal to 2, it's called a deep network. That's the usual way people say it. But there's a little bit of, like a gray area. People might mean slightly different things. Okay, so these empirical results basically suggested that the positive effects of using deep neural networks in practice that people observe have basically nothing to do with the pure approximation power of these deep neural networks. Okay, so question: in which cases a shallow neural network gives a better approximation than a deep neural network? Okay, so all I can say is by combining the theorems that I've outlined here, at least for ReLU networks, deeper is strictly better. Anything you can get with a shallow network, you can get with a deep network, and there are many things you can get with a deep network that you can't get with a shallow network. That's the kind of theorems that you get. But okay, if you change from ReLU to something else, there might be some other examples. I'm not 100% sure. Okay, so in fact, together with some other colleagues, we proved a set of theorems which tried to make precise the empirical results of Ba and Caruana. And what we did is we said, okay, let's just take ReLU networks at the start of training. So when the weights are random, these weight matrices W are just IID Gaussian random, like they are at the start of training when you use it in practice. Okay, so when sigma is the ReLU is piecewise linear, and therefore the whole function you get from X to the output is a piecewise linear function of X. And what we studied is things like how many pieces do these functions typically have? And what we proved was, at least, okay, originally to us kind of surprising, that the complexity of the random neural networks you get when you have ReLU activations is essentially meaning that the depth doesn't matter. It only has to do with the total number of neurons in the network, but now not how they're arranged. You can have one very wide layer, or you can have a bunch of deeper layers. It actually gives you the same thing. Okay, so the question is, are these results only for ReLU? So the answer is yes and no. So we did our results for any piecewise linear activation function. And that's the situation in which it makes sense to talk about these functions as being piecewise linear. And essentially, you can do kind of random convex geometry. Like when you plot these functions, they partition the input space of the x's into these convex regions. And over each convex region, they compute a linear function. And so you can ask, how many convex regions are you partitioning yourself into? That's the kind of questions we asked. So for other activations, I'm not 100% sure how to ask these questions. So maybe yes, maybe no. Thank you for the question. Okay, so this is basically all I wanted to say about approximation theory and the role of depth. Like, mathematically speaking, deeper is better, And there's a lot of beautiful and interesting math from my point of view. But practically speaking, the role of depth does not primarily seem to be that you enlarge the function space. It's more like I was saying before, these networks are so incredibly big that your function space basically has all the functions you can ever imagine in it. It's just that the choice of depth changes how you parameterize the space of functions. So it more influences how you do the search when you do optimization. Okay, so let me talk about that. Okay, so I want to give you a sense of what's the role of depth at initialization first, and then at least I'll vaguely say some things about the role of depth in neural network training. We actually don't understand it very well. Okay, so that's why I'm mainly going to build intuition here. And so for the people who are more like pure math people in the crowd, or dynamical systems people, or maybe PDE people, this is like the slide for you in a sense. Okay, so I want to tell you what I think is like a really cool analogy for thinking about neural networks. So again, I've written my neural network at the top, and I'm thinking about it at the start of training, where I'm just simplifying my notation. All the widths are equal to an integer little n, and my weight matrices are chosen at random. Just think of each component of the weight matrices as being IID Gaussian. Okay, so here's, for me, the best intuitive way of thinking about the effect of depth. And it's to draw two axes. Okay, I think of my neural network like a dynamical system, where the time one evolution of my dynamical system is go through one layer of the network. So multiply by a random matrix and apply your nonlinearity sigma. So in this way, L is like a time parameter, and deeper networks is like watching dynamical systems evolve for longer and longer times. Okay, on the other hand, N is like a system size. It's like the number of degrees of freedom. It's literally how many components I have that I'm watching evolve. Okay, and already from this point of view, you should see that N and L are going to fight each other, right? Bigger systems, systems with more degrees of freedom, take longer to come to equilibrium. And so that's the kind of basic setup. And just as a kind of like way of intuitively understanding what's happening, let's take the simplest case first, okay, where sigma is just the identity. So you can just remove the sigmas from the definition of the neural network. And what you see is that at the start of training, some kind of mental model for what neural networks look like is it's just a product of L plus 1 random matrices, okay, of size n by n. And what I want to point out is that mathematically speaking, such products of random matrices have been studied a lot, mainly in two regimes. Okay, the first regime is what I think of as the free probability regime. It's the regime where you fix the number of terms in your matrix product, you fix L, and you let the matrix size go to infinity. So it's kind of the top left part of this plot. Okay, this is a beautiful like world of things. It's all about maximum entropy distributions for eigenvalues, singular values of random matrices. Okay, so that's really nice. But there's another equally well-studied kind of regime for understanding products of random matrices. And this is what I call the ergodic regime. And this is like the situation of the multiplicative ergodic theorem, if you've ever heard of this, or like, Lyapunov exponents of dynamical systems. It's like long time stability in ergodic theory. So this is the situation where you have a fixed system that you're evolving, and you're watching it evolve for longer and longer and longer and longer. And okay, there's like an infinite number of papers written in these two regimes to try to understand just the matrix products. Okay, and one of the things I work on, and that's interesting for understanding the role of depth, is to turn on the nonlinearity and see what happens. Okay, and somehow what I want to advertise is neural networks are somehow in between. They can be both wide and deep, and making them deeper makes them kind of more chaotic. You're more in the ergodic regime, and making them wide kind of makes them nicer and nicer. Okay, I'm going to try to make that precise. So that's the first intuition for the role of depth. Depth can't be considered by itself. It has to be considered together with width. Okay, that's kind of where I'm going with what the effective depth of a neural network is. And so my summary, my second kind of intuition is that larger depth makes networks more complex, and wider networks, i.e. larger n, makes the networks more simple. And they fight each other in this manner. Okay, so that's just an intuition. And now I in the last kind of little bit of this talk, I would just want to say a couple of theorems and show you like one empirical result. Okay, I was told in every talk about neural networks, I have to show at least one experiment. Otherwise I failed. So I'm going to hopefully get there. Okay, so let me tell you about a really beautiful thing that happens when you take the width of the network, i.e. the size of the matrices, to be very, very large. Okay, so I call this linearization at infinite width. And the way I think about it is like this. okay, if you had 0 hidden layers, if L were 0, then your model Z of X theta is just a single weight matrix times X. Okay, that's also called the linear model. And so these are linear, and they have 2 very simple properties. Okay, at initialization, if you choose the weights, for example, to be IID Gaussian, then the way you start, the kind of functions of X you get at the start of training are just Gaussian processes. It's just Gaussians times an X. Okay, very nice. And they're linear models in the sense that they're linear models as a function of their parameters, right? There's only one weight matrix W, and it's linear in W. So they're extremely simple. And you might say, oh, deep neural networks are very different from this. But the theorem is that they're actually not. Okay, so let me state a whole collection of theorems, which is like where a lot of mathematical analysis of neural networks has been focused the last years. Okay, so if you fix any depth, capital L, L is now any number greater or equal to 1. So you fix the depth and you send all the hidden layer widths to infinity. So you fix the dimension of the x's, the inputs. You fix the dimension of the outputs. And then for each setting of the widths, the n1 up to nl, these are the dimensions of the w's, you get a random function from Rn0 to Rnl plus 1. And the amazing thing is that at infinite width, in the free probability regime, in the language of the previous slide, you get that neural networks behave like they're linear models. Okay, so at the start of training, the neural network converges to a Gaussian process. And moreover, throughout training, at least if your loss is something like the mean squared error, you can just replace it by its linearization around the start of training. And so in this way, you see that no matter how many layers in the network you have, you get a model which effectively has depth 0. Okay, that's kind of my TLDR for this slide. Infinite width networks are linear models. And this emphasizes what I said before. You cannot study the depth of a network by only considering the number of layers. It also has to do with the width of the network itself, okay, with the ends. Okay, so that's like my most theorem-heavy slide. I have to present these results because these are at the core of the starting point, at least, for the modern theory of neural networks. Okay, but let me now tell you how to actually measure the effective depth of a neural network. Okay, so again, I take a neural network with capital L hidden layers, and now I think of the width being large, but not infinitely large, because at infinite width, we saw that they have depth 0. Okay, I initialize my networks at the start of training in the way I've displayed in the upper right. You choose each of the weight matrices, their entries independently from a Gaussian with mean 0, okay, and a certain variance. This is just the right scaling for the variance. You can kind of ignore this point. This is how people initialize in practice. Okay, and then in a collection of papers that I wrote, sometimes by myself, sometimes with various co-authors, what we prove is that the right way to measure the depth of a neural network is not by the number of layers, but actually essentially as the ratio of the number of layers divided by the width of the network. Okay, or slightly more precisely, the effective depth of a neural network, at least in this fully connected setting, is given by the sum of the reciprocals of the hidden layer widths. That's what we find in various ways. Okay, so I'll show you an experiment about this in a second, but let me just say, when I say that this is the effective depth of a model, what I mean is that this is the parameter that determines how neural networks actually work. So for example, this is what controls how close you are to just being a linear model. Okay, so the way you reproduce the results in the previous slide is you fix the depth L, you let the width n go to infinity, and you see that while the apparent depth, the number of layers, was fixed, the effective depth goes to 0. And so you become a linear model. So it also controls this quantity L over n, the numerical stability of optimization. So it controls the variances of the values you compute and the gradients at the start of training. So if you're too deep, you won't be trainable, at least if you're too effectively deep, if L over n is too large. And it controls the amount of feature learning you do. Remember a bunch of slides ago, I said neural networks learn both a basis of functions and the coefficients in a linear combination at this basis. And so the extent to which that basis of functions actually gets learned is controlled by the effective depth, L over n. Okay, this is, of course, some relatively vague statements of precise results, but just ask me later if you're interested. And excuse me, please, I'll tell you exactly what I mean. Okay, so this is like, for me, like a prototype for how to understand the depth of a neural network. This is for fully connected networks. And there are many open questions when you start using more sophisticated neural networks that are used in practice. Okay, convolutional neural networks, residual networks, transformer-based networks. graph neural networks. There's all kinds of networks which are more complicated than the networks I've described here. And what the effective depth is an interesting mathematical question for many of them. And it really gives you practical recommendations about how to use these networks. It says, you want L over N to be positive, but not too big. You want it to be positive because you don't want to be a linear model, but you don't want it to be too big because when it's big, you're numerically unstable. There's like some actual real practical takeaways to all this. Okay, so let me conclude with the experiment that I promised you, and then I will essentially stop. So here's like a very, very down to earth, okay, from my point of view, illustration of why the effective depth controls how well you can train your network. So what you're looking at here is every dot is a very different kind of neural network trained on a very simple task called MNIST. Okay, MNIST, if you don't know, is a very simple task. It has 10 classes, which are the digits 0 through 9. And all we've done is we've plotted on the x-axis the effective depth of these networks, the sum of the reciprocals. So networks with the same effective depth, for instance, you can be twice as deep and twice as wide. So you look like a really different network, but you have the same value for the sum of the reciprocals of the hidden layer widths. So that's the x-axis. And the y-axis is basically how long it takes you to start training. It's the number of training steps or number of training epochs until you get to 20% accuracy. Okay, random chance accuracy on this task is 10%. And here I'm asking how long does it take to get to 20%? And what you find is that although the networks are extremely different that correspond to the same place on the x-axis, this sum of reciprocals is a really pretty good indicator for how long it takes to start training. Okay, so I see there's another question. How do you control the distance between the linear model in terms of effective depth? Right, so here's one way to do it. Okay, by definition, a model is linear if and only if its Hessian with respect to the parameters is equal to 0. Right, that's literally what a linear function is. And so you can ask, how large is the Hessian? Like, let's say the spectral norm of the Hessian of a neural network at the start of training, okay, of the output of the network with respect to the parameters. And when the dust settles and you do a bunch of calculations, you find, oh, interesting, like the size of the Hessian is actually a function of L over N, which goes to 0 when L over N goes to 0, but is positive when L over N is positive. That's kind of how that's one precise way to measure the distance to a linear model, but it's of course not the only way. Okay, cool. Okay, so this is my experiment. I was told to go for 45 minutes. So I'm going to stop here, and I'm happy to take more questions and have a discussion afterwards.
Okay, thank you, Boris, for this enlightening seminar, lecture. Very, very interesting. I have just a question. How to fix the effective depth in real problems?
Right.
It is the problem, no?
Okay, let me answer your question on two levels. So the first level in which I'll answer the question is that, before you know there's an effective depth, then for any particular problem, you're going to say, I need to choose a width and I need to choose a depth, and I might choose them separately. So now all of a sudden you learn, oh, maybe I should choose them together. So that already makes it much easier to do the choice in practice. And as you correctly point out, and this is the second way in which I want to answer the question, now there's a question of, okay, I give you a particular data set and a particular way of doing optimization. So how do you choose the effective depth? And the answer is, well, it's going to depend on the data. And I don't know how to make that match between the data and the effective depth. Okay, except in one case. I finished proving a set of results about Bayesian inference with neural networks recently. And what those results show, at least in a very simple case, they're just in the case where the nonlinearity is the identity. What you get is that you want the depth to be actually infinite. At infinite depth, what happens when you do Bayesian inference is you get the same posteriors as you would have if you had done what's called like empirical Bayes, i.e. you chose the best possible prior as a function of the data. So it's like, it turns out you can do two things. You can fix the architecture and choose the best prior as a function of the data, then you don't care how deep the network is. It works out well. Or you can fix a universal prior and just take infinitely deep networks. And they automatically give you the same posterior as the best posterior you could have gotten. And so at least in some settings, although I can't necessarily tell you what the right way to choose depth over width is, what I can tell you is depth over width needs to be positive. And in this way, like if you at least want large models, it means you have to take depth and width to infinity together. Okay, I hope that kind of answers the question.
Thank you, Boris. Very clear. There are other questions. I don't see in the chat other questions, but please don't be shy. This is a great occasion to. At the moment, no, a moment, there is another comment. Okay. Very interesting results. In your notion of effective depth, it appears that the order of the layer is irrelevant. 40 to 10 neurons or 10 to 40 should be the same. Is there an intuition behind it?
Yeah, so okay, that's an excellent question. You are very perceptive, and so honestly, when I was first deriving these results, I was very bothered by this point. And the first answer to say is you are correct. In these results, the order of the layers doesn't matter. Okay, there's always a but, right? Otherwise, it's not interesting. So the assumption in these results is that all the layers have the same order of magnitude. I didn't quite state everything precisely, but that there's a single large integer n, and all of the layer widths are between, let's say, n over 10 and 10 times n. Okay, so they're allowed to change, but they can't have drastically different orders of magnitude. Otherwise, things will be different. So that's the first thing that, although yes, in practice, when I actually do these experiments, it doesn't seem to matter very much the order of the layers, at least like without looking too closely. The theory really requires the layers to at least be comparable. And then the second thing to say is that if you look more deeply into the experiments and you really ask, not at the start of training, but at the end of training, how well does the network do, then the order of the layers matters very much. And the results I was presenting are really talking about right at the start of training, how quickly do you get going? How quickly do you do epsilon better than random? That's really what that experiment was about. It's not asking which network ultimately gives you the best performance. That's obviously very interesting, and I don't quite know how to do it. Okay, so there's another question. Often in practice.
Yes, there is another question. Often in practice, people use a stochastic gradient descent. Does this method affect your result?
Yeah, so that's a great question. And let me again try to answer it in two ways. So some of the results I presented are only about initialization. You haven't started training yet. You're just asking, what is the structure of the network right at the start of training and the structure of your gradients at the start of training? So in that sense, it doesn't matter if you're doing SGD or you're using Atom or I always assume you use a first order method to do optimization because that's what people use in practice. But there's a slightly more refined way of answering your question, which is that in practice, it is very important which first order method you use to do optimization. Like for natural language processing problems, all the modern neural networks have to use Atom, and SGD doesn't work that well. Whereas for computer vision problems, if you use ResNets, SGD is great and Atom's not so great. It's like, and we don't understand why. And so a lot of my results are not specific to the kind of optimizer because they're rather broad strokes. They say, if you do a network of a certain kind, you will be able to learn some kind of features. And the amount of feature learning that's going to happen is proportional or some function of L over N. But then if you ask me, what kinds of features are you going to learn? That will for sure depend on the details of your optimizer. And I don't know how to make that human computable. So it will depend, and okay.
Sorry, another question. If you choose different effective depth, you are changing the time to learn.
Yeah, so I think the question is based on the experiment that I showed at the end.
Yes.
So I wouldn't say it changes the time to learn. It changes the time until you start learning. So it's like the way to read that experiment is if your effective depth is too big at the start of training, you're just not numerically stable enough to do optimization. Like your gradients will either be 0 or they'll be plus infinity, roughly speaking. And so somehow you're going to be bouncing around for a long, long time until you accidentally make some good progress. And then once you make some good progress, learning will start. And so it's more like the point of that plot was to say, you don't want to have too big of an effective depth. Otherwise, you're just not going to be able to implement your optimizer on your computer. So kind of yes.
Okay. It seems to me there are no more questions. If confirmed, okay. Okay, time, yes, time was a computation.
Oh, I see. Great. Yeah, so that's a great question. And so the short answer is kind of. I mean, you can have the same effective depth, but you can have a network of depth 5, width 5, or depth 1,000, width 1,000, right? And like the computational complexity, just like literally number of flops for each forward and backward pass, is much bigger in the deeper and wider network. But in this formalism, I'm saying you're not going to get any different predictions. And so it's like, yeah, I don't know how to talk about the computational complexity of optimization from this point of view, although it's obviously an important thing. I mean, yeah.
Okay, thank you. All the people is thanking you because you have been really clear. If there are no more questions, it seems to me that we stopped with comments or questions. Okay, we can close the seminar. We thank again Boris, and we give appointment to the next week with Lorenzo Rosasco. Thank you everybody for being with us, and see you in 2 weeks.